joining us today. So just a few words about me. My name is Jastrzebski. As Viorika was saying, and my last name is Jastrzebski. I am a postdoc at New York University, and before that I was a PhD advised in particular by Jacek Tabor, who just gave a lecture at Jagiellonian. David?
Hi, nice to virtually meet you all. I'm David Szepesvari, and currently I'm a research engineer at DeepMind. Before that, I got a master's in computational statistics in Waterloo, Canada.
Cool. Yeah. So should we dive in?
Yeah, let's start.
Okay. So I can go through the overall structure, and I will be taking you through the first part, and then David will take you through the second part. So the tutorial is about autoencoders. These are a specific class of generative models, and this overall structure will be that we'll first implement the vanilla autoencoder, or the most basic model from the family. Then we will go through variational autoencoder, and at the end we'll look again at the vanilla autoencoder, but with added regularization, and we will look at all of these through the lenses of how good looking samples these models generate. And in particular, we'll be thinking about why vanilla autoencoders are bad at generating samples. We'll see why they might be seen as cheese, in the sense that they have holes in the latent space that don't enable them generating good samples, and how variational autoencoders can be seen as solving this issue. Few logistics. The structure will be that there will be exercises with assert statements that will allow you to evaluate that your solution is correct. And after there will be, like, let me quickly show you this. There will be 4 tasks, and like loading libraries. And after each, we'll be pausing, giving you time to complete the exercises, and we'll probably ask every so often a poll to see how you're doing. And at any time, please pose questions. And as we'll be waiting for you to complete the exercises, we'll also answer any questions. Feel free to ask any sort of question. There are no stupid questions. In particular, at least for me, it was a learning experience as well. I am mostly interested in optimization drug discovery, so I am by no means an expert on autoencoders. So I am and will be learning with you. Hopefully, David is more, knows better variational inference, so he will be taking you through the second part. Okay, so let's start. Let me know, is everything fine with size? I'm assuming yes, but please let us know if not. Oh, I should join the Slack channel. 1 second.
I guess in the meanwhile, I'd like to add that we do have a lot of questions as well in the collab for things to think about.
Yeah.
And I'd like to highlight that these are fairly open-ended. There's lots of possible answers, so don't feel like you have to get the right answer, but we would really like to encourage you to either on chat or like if you have someone to talk to a bit for a couple of minutes, discuss it with them, or at least write it down for yourself. Try to figure out how you would try to answer the question.
Yes. This tutorial is a bit less heavy on the coding side and a bit more heavy on like thinking and looking at samples. Okay, let's begin. So I will be doing the tutorial with you and pretending I am, able to solve all the solutions, but really copy them. So let's start. Okay, so this is. Oh, I should actually start from this cell. This is hidden, so this got me. Hopefully it didn't get you. So please load all the libraries. It will also install a Haiku library for you. This will take a second. Okay, I think we're done. This is not very important. It is just defining a few types for you and class labels. We'll be working today with a specific dataset called fashionist, which we'll soon visualize. Now I have evaluated 2 functions, or defined 2 functions. The first one, they are utility functions. The first one is a gallery. It's called gallery, and it will be showing you images in the matplotlib using matplotlib, and the second is loading the data set using TensorFlow datasets. So as I was saying, we'll be using the fashionless dataset. So you can here download it and inspect it. Please let me know if you have any questions with downloading it due to like too many connections or something. Okay, so this will take a second. We're using fashionless as opposed to list because this is just slightly more complex and shows a bit more and gives a bit more challenge to the models we'll be looking at. Okay, so at least for me it's done. Sorry, you might hear some knocking. It is New York and there is constant construction, and in particular in my apartment. Hopefully it's not too disturbing. Okay, so the data set looks like this. It's as David recently pointed out to me, it's mostly like sherds and boots, and one class that is different from these classes is a bag, which looks more like this, but most of them are either a form of like some top or a boot. So there will be sandals, ankle boots, a sneaker, shirt, pullover, and we visualize them using gallery function that we'll use throughout this notebook. Okay, so I'll just give like literally 1 minute for everyone to. If anyone has problem with downloading this, let me know. Yeah, so there is an asset, and as I said, just run it to make sure everything is fine. It should be fine. There was no coding, and we'll have assets like that throughout the notebook to make sure that your solution is correct. On this note, we will. David, I don't know if all of you noticed. David shared with you. Oh, right. I will actually share with you solutions in the meantime. Of course, for full learning experience, don't look at them. But if you are really stuck or you want to make sure that you're correct, this is for you. Okay, I posted in the Rocket channel, Rocket chat. Okay, I think we're good to go. Maybe I should spend just a few more seconds talking through the data. The classes, 10 classes, just like NIST. Shape of the data is also just like NIST, so it is, I believe, 28 by 28 pixels, or yes, I think so. Yes, 28 by 28. And each pixel, this is an important detail, will be between 0 and 1. So you can take this. Oh, sorry, you can take this and examine, for instance, maximum value along some pixel value. So this will take like around middle pixel. This is one channel, so there's only one channel. And if we look at max, like it should be below 1. And this will be important because in the section that David will be running, we'll need these pixels to be between 0 and 1 because we'll be interpreting them as probabilities. Okay, so let's start. I will talk a bit through the autoencoder. I will be repeating probably things that Jacek went through, and but I think that's fine. Autoencoders are neural networks that map their input into a new representation. So they take an image, if they are trained on or evaluated on images, and they take an image, they encode it, and typically they will be encoding it to a form of information bottleneck. So they want to reduce the number of information that they're able to store in the middle layer, and then the task is to decode the image, and hopefully that will be as similar to each other as possible. The reason there is an information bottleneck is because if there was no information bottleneck, for example, if there was the same number of neurons in the hidden layer as in the input or output, then it will be trivial to solve this task because you could just copy the image to the middle layer and then decode it by, again, an identity function. So we need a form of information bottleneck. Here it will be just using fewer neurons. On the image we have 2 neurons, and that's convenient because we'll be looking at models using 2 neurons. And in variational autoencoder, this information bottleneck comes in the form of adding noise to the latent space. And in other models, it can come in the form of adding a regularization. So for instance, hidden space will have a small effective dimensionality, which we'll look at in the homework part. More formally, if the input is X, the encoder is E and decoder is D, and the reconstruction is X hat is D of E of X, then the cost function of a typical autoencoder is the mean squared error function, which is basically the distance between X and decoded and encoded image. Again, to recap some of the things from the lectures, the space of representation is called the latent space, and we'll be referring to this many times during this tutorial. We'll be talking about holes in the latent space, on decoding from the latent space. So it's important to remember this name. By latent space will mean neurons in the middle of the network, basically, or what is the output of the encoder. And our first task from the 4 tasks that we'll have is simply to implement a Haiku module or class that implements encoder and decoder. So for an encoder with 1 hidden layer, the equation we will be interested in is as follows. So it's ReLU activation function, which I hope you are familiar with. It's a max of 0 and X of a linear transformation of X, and this gives you hidden, and then Z, so the final latent, is a linear transformation of that without any ReLU. And we'll use 2 hidden layers. So this equation is not exactly what you are supposed to implement. You're supposed to implement another iteration of this equation and then this equation. There is an effort that checks your implementation here. Your code is supposed to go here. You will iterate through each hidden size, transform it using Haiku linear layer, and then finally transform the resulting H using this equation, which again can be done using Haiku linear layer. The second task, and I will add both here, I will describe both, and then you will implement both, is to implement decoder, where essentially you're doing the same thing. You also will have a linear transformation followed by, with nonlinear activation, followed by a linear transformation into the input space. And this is the X hat that will go into the loss function at the end, or this is the reconstructed mushroom from the image at the top of the notebook. And you also have an asset that ensures that your implementation is correct, and please make sure it runs for your implementation. The asset has a lot of boilerplate, but don't be bothered by this. This is just because you're using Haiku here. And we'll then combine this into autoencoder, but this is not a coding exercise, just putting together what you came up with. But it's nice to see how your class will be used. So you will encode the image, decode the image, right? This is reconstruction. And to sample from a latent space, you just run decoder on Z. And that's it for this part. I will give you some time, between 5 and 10 minutes, I suppose. And then I will pretend that I'm solving this task as well by copying it from my solutions. OK, so any questions? So this is a good one to ask any question, really. And yeah, good luck. So not sure if I'm pronouncing it correctly. Mikola asked question, how do we know if autoencoder didn't copy the data? It's actually a fantastic question. This is the first thing that seems weird about autoencoder. So as I was saying, it has an information bottleneck. So we enforce it doesn't copy the data by disallowing it to put in, making it difficult for it to put, or impossible for it to put a lot of information in the latent space. In particular, we will be training in a minute or in a few minutes a model that has 500 input space, or 28 by 28, which is not sure if that's 500, but anyway, like large input space, and then this will be encoded into 2 neurons and then decoded. So you cannot keep in 2 neurons the whole image of a mushroom, right? That's at least this is the hope. So we're introducing a form of information bottleneck, and this comes in all sorts of flavors, from just using fewer neurons to like adding noise, as maybe you can interpret variational autoencoder if you wish. Yes, Adam mentioned that. That's that's true. It's true that if we had infinite numerical precision, that indeed, even in 2 neurons, you could encode as much information as you would like to. Thank you, Adam. That's a good point. Okay. David, could you, because I'm not that good with Rocket Chat, could you post poll for encoder just encoder implementation? We'll see how people are doing. We are not in a rush at all, so but just to know. How do you choose the activation function for the latent layer? No idea. I don't know. Not sure. I think the question of how do you pick, there are situations in which you have some sort of constraints or requirements, but in general, I don't think there's a good answer to what is activation function of a neural network. And in particular, I'm not sure if autoencoders have any have any recommendations really for activation function. David, do you have any thoughts on this question?
Yeah, I'm not sure about autoencoders or variational autoencoders specifically, but I guess ReLU has been becoming popular in general, though it also, at least from my experiences working with reinforcement learning, it also has its own issues, I guess specifically, I guess so-called saturating activations where once you are in the max 0 portion of the ReLU, you don't really get gradients.
Yeah, that's true. Yeah, I don't know. It's deep learning. No one understands it. So that's that's our answer. Okay. So people are working. No rush. Do we use linear haiku.linear? Yes, and use it like as many hidden layers there are, right? So if there are 2 hidden layers, use it twice or 3, including the call to construct z. Any suggestion about the choice of the size of the latent variable? If it needs to encode a longer sequence, will hierarchical VE help? Now that's a lot to unpack, but let me try. So in terms of size of the latent, for many reasons, it's a bit difficult to say anything more than that this is a hyperparameter. It's hard to evaluate like how much information you want to. I think this question is really similar logically to how large dropout should be. I mean, this is very similar of a question. It's hard to pick, hard to answer it in any sort of methodological way. Now, in terms of longer sequences and hierarchical VEs, well, in theory, hierarchical VE represents a hierarchical latent variable model, which is a very powerful model, but it's also quite challenging to train hierarchical VEs. So I'm not sure if it will help in general on more complex data, but it's certainly the hope of many research. It's a big research direction of how to learn hierarchy starting from hierarchical latent variable models. Okay, so how are we doing? So working. Could everyone please who is done with the encoder just add to the poll that David posted that you're done. We don't want to rush, but let's say when there are like 80% people done or something like that, we'll probably move slowly.
I guess my impression is that you can update the poll once you have finished it. Is that correct?
Yeah, I hope so. I will try to vote and see. I think so.
Right.
Yeah, I think so. You just click vote and then it moves you. Okay. Now let's wait a bit more, and I should actually copy solutions slowly or not?
Yeah, I think you can start to. There are a few other questions. Let me sample some.
Yeah, if you can pick one. I mean, so just tip. This should be the first line, right? Because you want to repeat the first, like in a recursive fashion. Recursive fashion, you want to repeat this first line. So this should go first. Okay. Do we have sort of interpretation of latent features in terms of variance, as in the case of PCA? Well, no, but sort of. I mean, you can associate how important the latent, because in PCA, by the way, PCA is literally, I think, literally linear autoencoder, right? So this is possible because in a linear model you can associate with one direction in the latent space the amount of error reduction. But because we have a nonlinear decoder, you cannot do it anymore in autoencoder. You could have a nonlinear autoencoder and then a linear decoder, then you could do it. But anyway, you can do like less, you can do a lot of things that are less theoretically justified than variance variance interpretation in PCA or linear autoencoders, when you can, for instance, measure importance of a given latent, right? And that's what people do, for instance, in VEs, where they just estimate the number of information in each latent neuron, and then they try to see which were ignored, let's say. So yes and no. Like, you can do things related to just feature interpretation, but there is no like super theoretically justified thing. Okay, so 68% are done. I will wait 2 more minutes and maybe pause in the question solution. So of course you should do the I mean, of course, but the first step is to do linear transformation, and then the next step is to do relu on that. Okay. You can, I mean, probably are familiar with Haiku, but it's kind of like stateless. So you can see that we are creating layers and not really keeping track of state. Yeah, and this should work. Let's see if that's true. So the way this check, so it should say congratulations, encoder implementation looks good, and the way it works is really simplistic. Like, it takes, what it does, it takes as input like a dummy 0 image, and it makes sure that it got encoded correctly to 2 dimensions, because we'll be using 2-dimensional latent space for interpretability. Now, let me go quickly through decoder. Let's see. Yeah, most people, okay, some people are still. David, do you think we should move on or wait a bit more?
Yeah, I guess, yeah, we can go to the decoder. I guess it's very similar.
So let me go through the decoder, then I will answer one more question, and then we'll move on.
Yeah, and I guess if the solution was not clear to someone,
yeah, I can talk about it. Okay, yeah, sure. Let me go quickly through solution of the encoder then. We repeat in a recursive fashion the first equation, and the first equation is 2 components, right? You do linear transformation, that's haiku.linear, and then you do a nonlinear activation function, and that's represented in the code here. So you do haiku.linear, and then you do jax and then .relu, and then we do the final transformation, which does not have nonlinearity, which is here. Now the solution to the decoder will be very similar. Well, we will also have hidden. Then, well, in this case we called it H, so we'll do like haiku linear of HS. We constructed the layer here, right? And now we call it on H. And then we need, and here we will be calling Jax, right? And on H. And then we'll construct, do the reconstruction, and we can just look at the equation. So it should be a linear transformation. One catch kind of is that you need to go to the correct output shape. So it's constructed neatly here. So there's that many pixels, right? So it's 28 by 28 by 1. So we do that. And we call it on H. And then there is one catch where we need to reshape this back to image size. It's kind of for convenience, maybe not necessary, strictly speaking. And Decoder is tested in a very related way, a similar way as previously. So the asset really goes through, like calls Decoder and makes sure that the output shape is as it should be. It's here 1414 because we constructed it as if the images were smaller, just to test that the implementation is not hard coding. Oh, okay. And this tutorial is difficult. One second. Okay, that maybe will work. Okay, this has worked. Okay, let me see and answer one question as I was saying. David, please let me know if there's like any question you would like to pick, but I can pick a random one.
I guess there were some more questions on the non-linearities, but I guess overall they all just have different properties, right? For example, different ranges, different shapes, which have an effect on how they map the inputs to the outputs, and different uses will call potentially for different non-linearities. Plus, sometimes you just search over them and see which one works best, right? Yeah. Sorry, it's deep learning. No good answer. So why do we define haiku layering call function? That's a good question, and I will take it. That's what I was referring to as haiku. I mean, Jax and haiku tries to keep this is by design stateless. So in particular, it is called like once, right? That's essentially what's going on, as far as I understand. David, is that correct? I think so, though certainly you can construct all of them in the constructor and just use them. Yeah, it is confusing. It is confusing, but I was learning Jax with you. I mean, I was voting maybe for PyTorch. I don't know, but anyway, that's my understanding that this is called once, and that's kept track of by the haiku framework. Yeah, it's a bit you can think about it a bit like as if you were constructing a computational graph in TensorFlow, in the sense that it's also called once and then reused. Well, that's my understanding. Okay, let's move on, I think. Yeah, I think that should be all right. Yeah, okay, let's move on. So we are combining this in an autoencoder. And the way we are doing it is very straightforward, as I was saying. We do encoder, decoder, right? As done the image with the mushroom. We encode the mushroom to like 2 neurons, we decode the mushroom, and we get something that hopefully has a loss of information in the middle, so it forces it to do something smart, And we do have here an information bottleneck because we're using finite precision probes. So we do have that. Okay, so training. For training, of any model, you need in particular loss function, the way to fetch data, construct the model, and we did all of that for you instead of the loss function. So the way I will go, let's assume for now that this is coded, and let's see how it will be used. And then you will have time to, code it and train your first autoencoder. And this will be the first outcome. So we will be using 2 hidden neurons. That's quite atypical, but we'll be interested in 2 neurons, in a model having 2 neurons, because we'll be able to visualize the latent and try to look at whether it has these holes, like how it looks, how you can generate from it. So it will make our life easier because we'll have 2 neurons, so we'll be able to use our visual intuition.
Here is a bit of a black magic that is related to answering a question about why it's called only once. So to create the model, we do haiku.transform, and here we do this magic that is, it will call only once this call function, right? Here. I think for the purposes of this tutorial, let's just assume it is as it is. I think that's fine. The tutorial is about autoencoders and not haiku. That's how you construct models in haiku. That's how I would put it, based on a class of the form as you were implementing. Now, we'll have an optimizer. We'll use Adam, which is one of the two most popular choices. The other one would be SGD. This is another helper function which takes your mean squared error loss and evaluates it on model output. Yeah, I think it will be worth going a bit more detail through this. I will do that in a second. Now you have here update function. Update function will be called in every iteration. If you're familiar with PyTorch, that's very similar to how PyTorch code looks. So let's go through each line. I think this is similar to what you have seen in other tutorials, or at least the supervised learning tutorial. So we compute the gradient of this function, of the loss function, evaluated on the current batch plus. Well, we need to pass parameters. Like, remember, it is stateless, and in particular, we pass everywhere params. That's a bit different from how we think about PyTorch in a way, or TensorFlow. So if we want to be as close as possible to the functional programming paradigm, we need to pass everything that's needed, right? And in particular, we pass here params everywhere, and everything returns params, right? So we pass params, we pass randomness key, and we pass batch, which will be used in a VE. It's not used in autoencoder. And we pass batch, which has images and labels, if you remember. Like, that's the keys that we have in that. And we compute update by calling the optimizer on grats. Well, optimizer needs grats, and it has its own state. Again, remember, it is kind of stateless. So we just pass along these things and evaluate and call functions on them. And these functions change these things, these objects. And then we have new params that we have optimizer.apply update. So this is, again, very similar to PyTorch, though a bit different in the sense that we pass all of these things along. And we finally return from these params optimization state and loss function. And if anything of that was confusing to you, let's look at the training loop, which I think will make all of this pretty much more intuitive. So here is a bit of boilerplate where we initialize random state, parameters, and optimization state. We load data set. So we have seen this data set. It says fashionist with there's all of these skirts and boots. And the optimization loop is very familiar and similar to that of one you would see in PyTorch, or other declarative approach to declarative type deep learning framework. So in each step, we'll update the parameters. So update takes current parameters because we update them. Next, random state. By the way, we are not using random state in autoencoder, but we will be using in variational autoencoder that David will be talking about. Optimization state, and the next batch from the data set. And then every 100 batches, we will be evaluating the model and plotting the images. So yeah, thanks for listening through this and following through this. And yeah, your task now is to implement this function. It is literally like one line that is mathematically represented here. And once you're done with that, please evaluate each cell, and you should see something like that. You should see images getting reconstructed. In the first step, you will see noise because the model is not trained well. It is not after one optimization step, so it just went from here to here. But after that, you should see more better images. And I think that's a good moment to stop. It's not much coding. Let's aim at around 5 to 10 minutes. The answer code is, yeah, David posted it. Sorry, it's not clear. Chris, if you have still problems with that, it's probably good to reach to one of the TAs. It's a bit specific. Let me look at different questions. Can we use something like CPy? Well, I think you have to use JAX, but feel free to correct me. I'm not very familiar with JAX. You should use JAX, right? Because as you call JAX is, so the theory behind, or the idea behind JAX is that this is like NumPy, but with keeping track of the necessary site variables, as you call NumPy variables, as you call operations on NumPy arrays. So, like if you use a NumPy call on this, it will lose track of the state and it will be unable to compute derivatives. But I might be wrong here. Like, feel free to correct me. Well, let's see. Not so fast. I didn't manage to copy code of Coder. I guess that's supposed to be me. If you have issues with following, check out the solutions that are. Maybe we should pin them. Like, can I pin stuff?
So I do think there are Google Meet set up with various TAs where you think you can show them your screen to make it easier to get help.
Sorry, could you repeat that?
I think there are some links on the website where you can go into a Google Meet, like we are in now, and you can share your screen and get help from one of the TAs.
Yeah. If you have issues like that, just reach out to teaching assistant. But answers are in the GitHub repository. But I feel like it would be nice to pin this or something like it, so it's easy to find. David, could you maybe in the middle just push it to the repository, the solutions, and it will be easy for people to find.
It is in the repository. I left the link. I'm just not sure, like you say, how to pin it.
Does it matter? Like if we have solutions in the GitHub repository, the official one, it should be easy for people to find.
Yeah, I think that's the case.
Okay, so just please go there and you will find solutions if you have any issue. Okay. Any other questions that I missed? So let me see. Are encoder and decoder stateless like haiku linear, or do we save them to self-encoder? We are saving them. Yeah, okay. We are saving them, but maybe we don't have to. So the question was, sorry, I should repeat the question. The question was whether we need to do this. I'm not super sure if we have to do that. I'm not super sure, to be honest. But I'm pretty sure it is correct to do that as well. Like, I'm not sure if we could go away with doing that. Like, one issue is that we are reusing decoder here and here. So maybe
I guess in checks they do probably end up stateless, right? Because you fetch the set of parameters.
Oh, right.
So on the other hand, the question is whether they refer to the same set of parameters or not. Yeah,
okay.
This definitely seems safer.
Okay, so based on my understanding, this is correct because you are passing parameters when you are calling sample and reconstruction.
Yeah, and I guess this way, I guess we make sure that once Haiku injects those parameters you pass, they are reused between the reconstruction and the sample, like you say.
Right. So there is Haiku doing behind-the-scenes injection of parameters that we should remember about. And my understanding is that you have to do that, for the Haiku framework to work well. There will be this type of you have to take by faith some of our implementations. Also, I didn't go in detail through the training group implementations. I hope that's fine. You can ask if you have any really bugging you questions. That's probably best to ask teacher assistant about the specifics of Haiku. Okay, so David, thanks for posting. Okay, so I think it's a good moment to go to questions. So there will be 2 questions, and I'll pause here. Oh, right, I forgot. Please add your code to visualize validation set. It's basically copying these 2 functions, so it should be fine. And in the meantime, so that so everything is clear, I will post implementation of the mean squared error. Then we'll go to the questions, and this will almost finalize task 2. So we need to just insert here the loss function. So it is very similar to what would you do with NumPy. Or I would say it's like the same, you just call it a different package. So it should be hopefully clear. So you have that. Then you call then you evaluate just our functions. Like you don't need to code anything here. Sorry, you also have to evaluate, of course, the encoder class. So this should be training and reconstructing every step, as I was saying. Now you need to here plot images. Okay, so this is training. We are not in a rush, so let me go through. Let's wait until it's done. You can see that with every step, the autoencoder produces better samples, and it's interesting to think about the learning process. Like, what does it learn first? It's just an interesting thing to ponder. Like, initially, it will learn like these kind of blobs, right? This is the strongest feature in the data set, which is learned first. And as David pointed out to me, it struggles with the bug class, which is interesting. Like, it does pretty well on other classes, but like it's like bug is not its forte. So it's interesting to think about this. I will just skip through this. Please implement it along the answering the questions. So the training, you should plot the loss function. You should make sure that your asset passes. And now, congratulations, if it passes, you have an autoencoder and you completed like a very important task in this workshop. And questions. So please answer all of these questions in the notebook. You can also send your answers to Rocket Chat, but the idea is that you answer them here, kind of for yourself. And in 5 minutes, we will go through like our idea what should be the answer. And as David was saying at the beginning, these are very open-ended. So there are no like bad, probably there are bad answers, but there are many good answers. So please finish training, add the visualization of images on validation set, answer questions, and then we'll go to task 3 out of 5 tasks that we have to do. And I will look through questions if there are any. Why copy code in cell 39?
I'm guessing maybe that's when we are visualizing reconstructions on the training and the validation sets.
Yeah.
It's just simple to copy it, but you're free to make it a function.
Yeah. We just wanted you to think a bit through what we are doing here and force you to think by copying some of the code or like restructuring a bit to be run on validation set. Okay. Is JAX power 2.0 faster than? No, I don't think it is. I mean, no, I think Python just will I think JAX overloads power and calls literally JNP power. A bit of off-topic question: why activation functions are in JAX and not in Haiku? Well, I don't know. I mean, it's.
I can answer this. So I guess JAX is kind of like a bit more low-level thing that does automatic differentiation for you and compiles things on the GPU and so on. So it's great at doing these, and they already provide some activation functions. And then Haiku was basically something added on top to. I guess some people thought it's easier to use Haiku to express certain things, but JAX already has the activation function, so we don't need to copy it into Haiku.
Yeah. Like JAX is basically NumPy plus AutoDiff. That's what I would say. And as such, from this perspective, it's not it's not supposed to have more than that. And I guess activation function falls still squarely into this basic building blocks space. Any other questions? So there is an issue of training. I feel this is better for a teaching assistant. Yes, Haiku is on top of JAX, yes. I don't see any other questions. If you posted a question, I didn't answer it, you can just like repost it. And I will give it like 2 more minutes or 3. Please remember to write answers to the questions.
Yeah, in terms of training not being correct, we do have these asserts to try to check things on the code, but I guess they are not non-comprehensive. So just because some assert passed, it doesn't necessarily mean that section is perfect. Yeah. Let me put a poll up.
Oh, yeah, thanks. That will be helpful. Does Haiku JAX support distributed training? Well, I think that's one of the point of the existence of Haiku. As far as I understand, Haiku is supports this type of things, and there are examples in the Haiku repository, if I remember correctly, that are distributed between GPUs or TPUs. So, and JAX, no, JAX is like it's not the purpose of JAX. Yeah. Would making autoencoder for color images change the architecture beyond changing the shape of encoder and decoder? Well, no, not really, in the sense that you can just always flatten, but it is, it is good to use convolutions if you are dealing with images in general, both RGB and normal. Okay, it seems like,
yeah, I guess just to add a little bit to that. Sorry.
Yeah. Sure.
In practice, you would use definitely more expressive models, and your latent size also would not be too it's too small. And the reason we are doing that is to make it easy to visualize the latent space. But in practice, you would definitely use a larger latent space, more expressive and models, as well as convolutions, like you said.
Yeah. It's a very toy task, models. This has to be clear. It's definitely not representative of the size of autoencoders people will train. Okay, let me go quickly through my take on the questions, and then we'll move to the final task with me. And yeah, so what can you say given the training loss and validation loss you see? Well, I don't see overfitting. That's good. I think that means we didn't stop training too late. Do you think do you think overall this works well? This is an open-ended question, right? I mean, I don't know. For bugs, it doesn't work too well. Yeah. All right. Do you see some systematic problems? Well, I think one systematic problem is that we didn't use an architecture that is like well adapted to images, and that's a systematic problem. David, do you have a different answer in mind?
I guess one of the things was the bag.
Yeah.
In terms of not being able to reconstruct that so well. Yeah, so I don't know if people got a chance to think about that. Maybe we can give them like 2-3 minutes to think why it is particularly that the bags are poorly reconstructed while the others seem.
Sure. Yeah, I think this is the only question that. Well, I think it has a well-defined answer, and this answer is kind of interesting. So 1 minute for that, and we'll move on to leave enough time to go through variation autoencoder. Yeah. Okay, so 1 minute for that. And also think about how would you sample a new image? Like imagine you want to design a new bug, and how do you use maybe not bug, like bugs don't work well. But like, let's say you want to design a new dress, and how would you do that using the autoencoder that we have? The functions implemented in the autoencoder object might give it away. So please think as well about this, because that's what we'll dive into in a second. You don't see overfitting. Validation and training loss are so similar. That's suspicious. Well, how is overfitting defined? Like, the definition of overfitting we had in this case in mind is that there exists a hypothesis that achieves a better validation loss but a worse training loss in the hypothesis space, and you pick not that one. Like, that's the definition I had in mind. And of course, while it's difficult to prove, I can definitely say that there is a hypothesis class, meaning weights of the autoencoder for which training loss goes down but validation loss goes up. So in this sense, it is not overfitting. That I don't see the one giveaway of overfitting, which is that training loss goes down but validation loss doesn't. So in this sense, it's not overfitting, but well, it's not super strict.
I think part of that is our model is not so powerful.
Yeah,
so it has a strong inductive bias. It generalizes pretty decently over the space.
Yeah,
doesn't have a chance to memorize the training.
Yeah, but this is a good question in the sense that it's not well defined what we mean by overfitting in general. But like, you can say different things that are overfitting. And well, in the definition that I mentioned, like, it's not clear. In the definition that training loss is much lower than validation loss, it's clearly not overfitting, right? And I think that's the most common definition. Okay, let's go through it. So why do you think bugs are poorly reconstructed? Our model answer, or David's model answer, is that just bugs are the only class that's very different from other classes. The idea is that codes, the majority of classes are either like a form of boot or a form of something that covers large part of the image and looks like this. And then bugs have more variability within class. There are some bugs that are covering more of the image, and there are some bugs that cover less of an image. And I think that's the model answer. It's not something we have scientifically thought through, but it definitely felt like that. Like, this can be a bug, and also a bug can cover only half of the image, and this is rarely the case with other images. We can test a hypothesis on our part, but I think it's interesting to think about it. Okay, the final part with me. So we train an autoencoder with 2D latent space. So we can visualize easily what latent looks like. We will plot the Z for 10 batches on validation set and color them by their class. And before looking at how it looks, just give yourself a moment to think about how it will look. And in particular, there are 3 questions to ponder. Do you expect data from the same class to be close to each other? Can you think of some choices in our model that has an effect on the latent space? And what parts of the latent space will be covered? And in particular, will be there holes in the latent space. And holes in the latent space, or parts of the latent space, what we mean by holes here is that the density of this distribution, or the number of points from this set of Z falling in this region, is 0 or very small. So that's why we call them holes. More formally, they can be defined as regions of low density in the latent space. All right, so just 1 minute. Maybe for these particular questions, you don't need to write them down, but feel free to just think about them for like a few minutes or 1 minute.
Speak to yourself.
Yeah. Is the fact that we are not overfitting a hint that more expressive models could perform better here? Yes, typically yes. I mean, typically in deep learning, you want to have an expressive enough model that allows you overfitting. It's one of the key lessons of deep learning. And it's also kind of weird why this is the case, but yes, if I were like working on this data set in some more professional, like in some context like of a research project or for a company, I would definitely try more expressive models, yes. Is there any way we can find a part of latent space that corresponds to a concrete type of the image? I suppose you mean class, or right? If yes, you can like do clustering on the latent space with class information. That's one way. So let's go through it. Let's see. So if you look at it, that's how it looks. So the red cross marks kind of arbitrarily, though not completely arbitrarily, 0.00. And it's nice to see that at that point there is zero density. So there is like a hole in this point, meaning that we don't really have an expectation for what will happen if we decode from this point. Now, color represents the class. So do we think that, do we see that the similar classes are close to each other? Yes, they are. Now, why they are close to each other is that this is then simpler for the decoder to reconstruct, right? Because it has it is an easier task for the autoencoder, for the decoder to reconstruct correctly if it can assume, right, that close stuff is similar in class, right? It's just an easier learning problem. Or more precisely, because we don't have here class information, I should say that it's easier for decoder to decode or do its job if images that are close in latent space are visually close in the loss function that we used. And it's interesting to think about how different architectural choices potentially impact this. So if you have a very, very powerful decoder, right, it by the logic of what I said, or following the train of thought that I had, if you have a very powerful decoder, you can forego this continuity in the latent space with respect to class, because your decoder will be able to like pick a small part of the latent space and decode a specific image. So you can have a form of memorization in autoencoders as well, where memorization is that there are very specific regions that are disconnected between different regions. So long story short, if you have a very expressive decoder, you can expect that you have less continuity in the latent space. Or at least this is plausible, it happens. So what was the other two questions, or the other one question? Which parts of the latent space will be covered? Yeah, that's the point. There is no theoretical reason for, I mean, there are some, but generally speaking, there are no very clear theoretical reasons for a given region to be covered or not. Of course, you can think about that it is easier for the model to cover this part of the latent than, let's say, some part very far from 0, 0. But there are no explicit, I should say, constraints on the model to put something in a given place. So it's a bit more difficult to sample from it. Okay, so let me see if I missed anything. Yeah, so it's interesting to think about whether a random seed will change this image considerably. We saw it to change a lot, but the overall fact that there are large holes in the latent space close to 0, 0 seem to remain with us. And finally, we have here a bunch of boiler code that enables sampling from the model. It's basically using the sample function. That's why I referred to that the classes that we implement might give away how to sample from an autoencoder. So it's simply calling a sample from a V that you picked manually from this 2D dimension. So like you pick this cross, you pass 0, 0 through this function, you get an image. That's pretty cool. We need params, so we just use we'll use the trained autoencoder. So you'll make sure that you have trained your autoencoder. Yeah, don't look at the result. We forgot to remove it. So boiler code. And now what you can do is you can sample from your autoencoder like this. So you do x reconstructed equals like sampler apply parameters. You need to pass correct parameters and z that you wish to decode. So your final task with me is to decode a few images, and in particular, please decode from this red cross. See what are the results. Don't look at these results. And think about, okay, there are two questions really that I want you to answer in this final part with me. Why do you think the example from 0, 0 looks like it does? And do you think there is any process to better sample? If you were a designer that is tasked with designing new clothes using this autoencoder, which would be weird, but actually people start to use in the creative process models that are related to this, like unsupervised learning models. So let's say you are tasked with generating a new shirt from this, or maybe any image that is a garment. And how would you do it better than what we did? And can you automate the process of picking latents and decode good images? Okay, so like 5 minutes, and then I will answer these questions from my perspective and hand over the tutorial to David. Okay. So I will just read the most recent question. If the vanilla VE cannot work well for a long sequence generation, will VQ-VAE be more promising? I don't know. I feel like Adam will know. Oh, Adam started answering, so I predicted that well. I will leave it to Adam. I don't know. Sandals also have more. Yes, that's what I thought about sandals as well. Actually, just on the back of my in the back of my head. I don't know. Maybe sandals also don't work well. It's worth checking if what we said made sense or not. I think that's a good point. That's a good point. If the argument works for bugs, it also works for sandals. True. How do encoder decoder should look like for more realistic data sets? Let's say I have 1,000 images of my cat. Well, that's a realistic data set. Okay, I have 1,000 images of my cat, and I want to generate thousands of new ones. Could you elaborate on architectures? That's a question about what the state of the art in image generation, because your question wasn't like very specific to your data set. And as such, it's a very fast-moving field that I think that this question is best answered by the lectures that were before this tutorial. Like I would just say that there were if you want to generate a lot of like interesting images, clearly a well-trained GAN is capable of that, given results in the Big GAN paper. But there are many other architectures that are also doing increasingly well. So I think it's more like a question of what is state of the art in generation, because you didn't say anything very specific to the data set. And also, like, I'm not an expert in unsupervised learning, so that's how I would answer it. Definitely not what we gave. As for are autoencoders capable of giving very strong, well-looking images? Well, maybe not autoencoders like that, but well, for instance, autoencoders based on VQ, autoencoders like based on like VQ, VAE, for instance, is a class of models that is more capable of generating realistically looking examples, because they are storing in the exact copies of the images. But that's a longer topic. I think I would have to go through lectures to answer it well. What's the problem with reconstructing bugs? Is there too much info that does not fit into the bottleneck? In terms of reconstructing on the training set, yes, in the sense that we have very limited info. Like, it's also interesting here to think about how models learn. So they will first learn what is easiest. Deep models and in general machine learning models are just super lazy. Like, they feed first the simplest patterns in the data. And clearly, it's easier to output a blob for a class than output two different blobs depending on a sub part of the class. So I would say that the simplest information is not the one that is most useful for reconstructing bugs. And now, in terms of if increasing capacity would enable reconstructing bugs, clearly yes, in the sense that you will get lower reconstruction loss on the training set, but I don't know if it will generalize better, and I think that's an interesting experiment to learn. Why top right corner is empty? The model could do better, less overlapping if it used the whole space. I don't know if it would do it better. I'm not sure if it would. Maybe not sure. Maybe it comes partially from, that's an interesting question, actually. Maybe it comes a bit from the ReLU function, because ReLU function will do this type of partitions of the latent space, right? Because it zeroes out a large portion. So maybe it's due to the ReLU. Maybe try another activation function to tie back to our discussion on activation function. Maybe it will do something different to the latent space. Interesting to look at, to think about. Is it possible to make the access of the latent space more interpretable? Now that's a deep that's a very deep question. These entangled representations, like beta VAE is the closest one to what we looked at. It's a good starting point to examine this question. But it is like you open a can of worms in a way. Like, that's a whole research area. That's actually very strongly debated right now. Maybe you can, for instance, look at the best paper award from ICML last year, where they were experimenting with the utility of interpretability in like disentangled representations. Okay, do we have a poll? No, not yet. Or should we have a poll? Maybe not necessarily.
Yeah, I guess we can discuss.
Yeah, I agree. So the results are like this, if you didn't look yet. So if we decode from the 0, 0, which are these two images, just let me make sure that they are the actual images. Yeah, so if we decode from, I will just post code so it is clear for all of you, right? Because this code is actually a bit more complex. So I will go for code first. I think that's the best structure. So we will decode 6 images, and you can see 6 images here, right? 0, 0, 0, 1, 0, -1. So let's look at the image and see what we should expect. So we decode here, and we decode here. So we should see in the third image something, right? Because we decode from a space that has some density. And that's what we get, I suppose. Yes. So here we have these random, ghostly, or even scary images, or like memories that the model has. One way to think about this is that this is like the mean class. If you look at this image like very closely and like want to believe this, it has here
Sorry, that was me.
sure. It has here the envelope of shirt or like t-shirt, and here you can see some boot. So it's kind of trying to do its best, right? It sees remnants of few classes. And here you can actually target specific classes by like manually looking at the image and like going, okay, I want here, and then you can sample dress, right? And you kind of succeeded to sample a dress to quickly answer the questions. How could we automate the process? Well, there are many ways to estimate the density of the latent space. So imagine you have a density function here, so something that goes from 0 to 1, and then you can sample from this density, right? So you can run a density estimation on this, like any density you wish, like kernel-based, like whatever. You can run a kernel density estimation here and sample from that. The simplest example of density estimation, perhaps, is to fit a Gaussian distribution, so fit mean and fit standard deviation, and this is actually what will be part of the homework. Okay, so thank you very much for going with this with me, and David will take you through the last 2 tasks.
All right, let me see if I can share the screen.
Oh yeah, I have to unshare. 1 second. Okay.
Oh, okay. I have way too many tabs to choose from.
Okay.
This one, I think. Can you all see?
Works for me. You can zoom in a bit, I guess.
All right. Does that work?
Works for me. Hopefully for others as well.
Okay, cool. So I guess we learned all about autoencoders in pretty good detail, and we'll move on to variational autoencoders, which are in structure very similar to an autoencoder. They still have an encoder, a decoder, and they also try to reproduce data, though we do the additional thing here of trying to learn the actual distribution of our data as opposed to just reconstructing individual images. And with this, we get encoders and decoders that are stochastic, and we get to think about distributions both in the data space and in the latent space. So while this is structured quite similarly, the story does get a bit more complex just because there's a few more elements to think about. And I wanted to start with introducing basically the characters in this story. The first thing of importance is P star, the true data distribution. And in practice, we have samples from this, our training set, our independent samples from this distribution, our validation and test sets as well. Then we have a so-called prior over the latent space, and this is denoted by P of Z. And we still have our encoder and decoder. So the encoder still retains its role of taking an input image and then spitting out something over the latent space, but in this case, it's spitting out a distribution as opposed to just one specific latent. And this will be denoted by Q phi, the conditional distribution of Z given that particular encoded image. And this is called the approximate posterior distribution, though the approximate bit is often dropped. And there is, I guess, a lot of terminology here, but a bit later on, it will make more sense as a bigger picture. And finally, the decoder again can be stochastic. And in this case, it's modeling the likelihood distribution, which is the X, like a conditional distribution on X given the particulars that we are decoding. And the decoder will be parameterized by parameters data. Just to take things step by step, first what we do is go through the reconstruction and the sampling procedures in a variational autoencoder visually as well, just so that we kind of get to know these characters a bit better. So on this diagram, we will have both reconstruction and sampling. For reconstruction, let's just focus on this lower area with, I guess, the blue items. So we start by taking an example from our true distribution. I guess here I call it x0, but say x2. This side is the data space. So we sample an example, say an image, and we encode it into the latent space. And it turns into what will be, I guess, generally a distribution, but it will be kind of a special Gaussian distribution with some mean and some variance or covariance matrix. So this is our posterior Q phi. And again, it's a distribution over the latent space conditioned on the particular example. Now, in order to actually get like a reconstruction image, we now take a sample from this distribution. Now, we could also, like, an option is to take the mean, but we can also just sample from this distribution and then decode it. And this brings us back through the likelihood function into data space, where we get a distribution over the images, right? And finally, we can sample a reconstruction form from this. Yep. And then, yeah, our final result is again in images. Now, yeah, you can do this procedure for some other example. Again, we would map into a distribution over the latent space, sample there, and then we map back to the images. I want to stop and ask if that makes sense generally to people.
Yeah, if you have any questions, ask them on Rocket Chat. And this is a difficult concept, so it's perfectly fine if something is unclear.
Yeah, I guess everything after this will involve these concepts, so it's important to make sure we understand them now. All right, so far I have 100% success. Cool. And yeah. Okay. So for the people for whom it doesn't make sense, do you have some specific questions that might help clear things up?
Yeah, if you have a specific question, what doesn't make sense, it's good to put.
Yeah. Okay. So that's indeed a very good question, and it's a typo. Let me fix it. It is so. The question was whether the x0 in step 1 and step 5 are the same, and they are definitely not the same.
Yeah.
So the second one should have like an apostrophe or something. though generally we do want them to be similar. Yeah, thank you for that question.
Yeah. Nice results on latent space. Trying different activation functions. That's a lot of fun. To answer, maybe I can take the question about reconstruction. The question is, do we sample from a Gaussian whose mean is that point and variance is 1? Yeah. I mean, no, sorry.
Yeah.
The point is that, and the variance is given by another linear function in haiku, right? So you both compute mean and variance from which you will sample.
Yeah, so this distribution can have a learnable variance as well. And I guess I didn't do, well, that's all right. So in this image, you can actually see, say, the green Gaussian distribution. The axis, one of them is a bit longer than the other. So even in the different latent dimensions, you can have different variances, not just a variance of one. Though of course, you can also try fixing it at one. But for the traditional standard variational autoencoder, you will learn these variances. Okay, I'll also talk about sampling, and then that might help clear some more things up if there's still confusions. Okay, for sampling, basically, that's still going to be pretty simple, and it is reminiscent of our data generation in the autoencoder. In this case, we have this black. Well, this is a black circle here that is representing a standard normal. So 0 mean and unit variance normal, and we will take a sample latent in this from this Gaussian like standard normal distribution, and then such as this set prime over here, and then decode it using our decoder, which again outputs a distribution, and we can sample from that. Yeah. Let me check some of the questions. Yeah. Okay. Yeah. So there was a question that Stan just answered on using Gaussians is definitely putting knowledge or an inductive bias into our model, and it can be also restrictive, but it allows us to actually train these, and you can replace them for a bit more complicated models. But in general, there is a trade-off between what models you can work with and how much expressivity they might have. Okay. All right. So I think most people are fine with this, and yeah, just to make it specific, in the standard, like I guess original VA paper, and what we're going to do, and what is often done, the encoder is basically multivariate Gaussian over the latent space with a diagonal covariance matrix, which is equivalent to each latent dimension being a univariate Gaussian with some parameter, like with some mean and standard deviation. And we are going to parameterize this mean and standard deviation, and that's how we are going to learn the distribution. Okay, and you will see exactly what that means in code soon, since I think you'll have to do it. And for the decoder, we'll actually change the data a little bit. And there's multiple options here. I'll present the one that we are doing, and then we can talk about others. We will definitely quantize the pixels into 0 and 1. And then the encoder model's output is going to be a Bernoulli distribution over each of these pixels. So Bernoulli, you basically output 0, 1 with some probability. And that's how we're going to model the pixels. And yep. Okay, so modeling wise, before we go on and talk about how to train the variational autoencoder, we'll just implement a model to kind of, yeah, I guess we know everything on how to actually implement the model, so let's do it. So again, we'll use an encoder very similar to the autoencoder. So it will be two hidden linear before mapping into a latent space. But now we wanted to output a Gaussian distribution. So what we do is basically have some shared computation towards some hiddens. And then we kind of split that hidden into a mean and something representing the variance, right, with some linear maps. So this first line is the one calculating the mean from this hidden, and then the second line is calculating some function of the variance from the same hidden. Okay, and then we can just use the outputs, which are vectors of latent size, in a normal so that we can sample from that. So yeah, so there was just this question, why do we train for log sigma and not sigma directly? And that's exactly my question as well. Can you perhaps think about why we would do that? Just for a minute, and then we can discuss. All right. So you probably had a bit of time to think about it. There's one of the main considerations is that we want the variance to be non-negative or positive. So if we interpret the output of the network as log sigma, we can exponentiate it, and that way we can guarantee that it is positive. And I mean, that can tell you, oh, well, why don't we just take the absolute value or something like that? So that's where the second consideration comes in, where I think actually someone mentioned it does, having that exponential shape does help with numerical stability and also gradients. So the shape of the function matters. There is another alternative I've seen used multiple times called the soft plus, I think, which is a lot like the ReLU. It's just like smoothened out around, I guess, around 0. Oh, I already have the solution. So just don't look at the screen for a second. Okay. So the first exercise is basically we have the hiddens calculated, and you need to implement computing the mean and the log of the standard deviation, or actually the standard deviation from that using these linear layers. I'll give you a couple of minutes to do this before we move on. Stan, have you seen some interesting questions? I see you're answering a lot of them, and you're muted.
I'm answering some of them. Let me see. I think no. One question that is worth discussing with everyone is, David, if you could answer why, if we are using, oh no, that I think you answered this one. If putting Gaussian is, you answered the one about Gaussian. Besides that, oh, there is one question. Does it make sense? Oh, that's a good one. Does it make sense to consider non-diagonal covariance matrix for QP, Q5?
I don't know. Do you have opinions on that?
I think I would just say that the fact that prior is, oh, this is more precisely about the encoder. Yeah. Well, I think there are papers around that. I think it is a bit restrictive, but I think that the main issue is that if you were to change something in expressivity of the variational autoencoder, I would go more in the direction of the other question, which is maybe we should make the prior more complex, because even if you make Q phi more complex, the term will drive your Q phi to be anyway a Gauss. So I think that if expressivity of your encoder distribution is an issue, then probably a good starting point would be to make the prior more complex, because Q phi can be pretty complex in the sense that it can make the sigma, the predicted sigma, which describes the Gaussian from which you will sample, very small, and then it can be very expressive when combined with all of the samples. So I would answer it from this perspective, that you could look at it, for example, the paper called Adversarial Autoencoders. It's just one example of making the prior more complex.
Yeah, I guess that's certainly possible.
Yeah.
So there was also this question: can we apply ReLU to sigma instead of predicting log sigma to keep variance positive? And I understand the gradients don't flow when the prediction is below 0 in the ReLU case. Does it matter in practice? I guess my impression is that it is better for, I guess, numerical reasons to have that smoothness. I haven't actually tried using ReLU. I'm not sure, like driving. Sorry.
There's another argument. Let me complement. So one is that you keep it positive. Another one is that if you predict log, then you can more easily, implement a model or learn a model that predicts Q phi with different scales for different examples. I'm not sure if that's important in a VE to work well, but at least that's this expressivity, which using just ReLU wouldn't. Oh, sorry, you were saying, can I apply ReLU to sigma instead of predicting log? Oh no, okay, I answered the correct question. Okay, so I think that's another reason we do predict log sigma. But it's interesting to see how the model would perform if we remove that experiment.
Yeah, I think that driving. I feel like if it's actually like not smoothened out, you can easily get to 0, at which point your distribution kind of like collapsed, which I think would be problematic, especially if you cannot get out of there.
Oh, that's a fantastic insight. Yes, so yeah, I agree. So just to repeat what you said, so if you have exactly 0 as sigma, that's also bad, because then I think, well, I'm not sure how exactly the KL term looks, but it's probably problematic for it.
Yeah. Okay, and there was also a question on why this should work better, sampling from distribution, and that's a great question. And soon, once we get into training, I guess I can hopefully motivate better why is it that we are using variational autoencoders instead of just autoencoders. All right, so I guess everyone actually had the code, so let's just put it back. And just to make sure we understand what happens here, we literally pass our hidden layer through a linear in order to get the mean, and similarly to get the log standard deviation, and finally we exponentiate it, turn that into a standard deviation. Cool, let's run that. And then now let's turn to the decoder. Now, the decoder itself, we can just reuse from the autoencoder. However, the outputs there again can be any number, like any real number technically. So, but the Bernoulli distribution, we want to parameterize it. The parameter has to be between 0 and 1. So what we do is we pass the output from the decoder through a sigmoid, which will smoothly bring it into the 0-1 range. I guess the sigmoid looks kind of like this, between 0 and 1. And so in the cell below, we'll have two things to do. The first one is a bit just code-wise. The second one is a bit more interesting. So first, in the reconstruct function, you need to combine basically self-encode and self-decode in order to output all of these different quantities. And this should basically correspond to the picture, and just check what encode takes as input, it takes as an image, what it outputs. It outputs the mean and the standard deviation of the resulting Gaussian that you're learning, as well as the sample set. Oh no, that should have not been there either. Yeah, and the decode, it takes a latent, and then it goes through the procedure we just talked about, and we output, like, we generate two things from this. First, we have the logits. From the logits, we pass it through the sigmoid to get the parameters. This we can also call the mean image, because it's basically going to be the mean of all the samples due to how the Bernoulli works. And then we actually sample an image, and we just return both of these. So that's we need to combine these two functions for the reconstruct function. And then the other one, I do ask you to remove the code and then read through this text if possible. But what we do, just to go over it, is in order to take a sample from the Gaussian distribution that's parameterized, we do this, I guess, kind of trick where we sample from a standard normal Gaussian. So the standard normal Gaussian has zero mean and then unit variance, and then scale and shift that sample so that it looks like it's from normal with that particular mean and standard deviation, right? And there's actually some algebra you can do with Gaussian distributions, which is outlined here. So if you have some sample from a Gaussian distribution with these parameters, if you scale that sample, now it's going to be distributed according to a normal with these parameters. And similarly, if you add a constant to that sample, now it's going to be as if it was a sample from these parameters. So you just need to figure out how to turn a sample from this one into this one using these rules. Yeah. And I guess one thing to mention is this shifting and scaling shows up in a lot of variational autoencoder literature as called the parameterization trick, a reparameterization trick.
If you're done with the question, please, with implementation, please answer the poll. And I guess it's a good moment to ask any questions if you have.
Oh, I already copied in the answer. All right, it looks like people have finished. So just to go over it with everyone, what we do is basically call encode on the image, and this will give us a sample, the mean and the standard deviation of the Gaussian distribution that we're learning, the posterior. And then we use that sample to decode according to our procedure earlier, and that will give us the logits, the parameters for the Bernoulli as well as the sample, and we just return these. And then this other bit, unfortunately, was already there. But yeah, you just need to use these rules in order to scale the normal sample by standard deviation. And I guess one key thing to notice here is that we are scaling this by a standard deviation, and because of this rule, the sample will actually be coming from, like the standard deviation will be squared. It will show up as standard deviation squared, which is what we want. Then we just add the mean to shift it like this. Okay, so let's run this. Let's there's a check after it. Let's run that to see if our VA implementation is reasonable, and come to the loss. All right. So in order to discuss where the loss comes from and what it means, let's recall what we want to achieve with the variational autoencoder. We want to learn the distribution of the true data, right? So we want our sampling model, just to recall, when we sample latents from the prior and then decode those, to match the true data closely. So what we do is we use the maximum likelihood training to maximize this expectation. So what does this say? We take our data from the two distribution and then check how likely our model thinks this data is. And we just want to maximize this by tweaking our model. Right? I believe this is also called the evidence. Now, note that this P theta x, I guess it didn't explicitly show up before, but it's the marginal probability distribution. So it's really summing over summing over the latents. And we can rewrite this joint distribution in familiar terms, like so. So this is saying this is our prior, and this is our decoder, right? So this really corresponds to our sampling model. Okay, so that's great, but in practice we cannot actually compute and maximize this quantity, and it's just not feasible for most cases. In some small cases, you might be able to do it, but not for a variational autoencoder. Often it's problematic. So instead, what we do, we introduce this approximate posterior, the encoder that we talked about, and can do a bit of mathematics to show that this inequality holds. And we are not going to we will not derive this inequality. However, let's discuss it. This the right-hand side here is called the evidence lower bound, often referred to as the elbow. And I guess this thing shows up like this technique of introducing an approximate posterior distribution and using the elbow together. That does show up a bunch of times, and this is what's called variational methods or variational inference when we mean kind of figuring out the latents corresponding to an image. And that's where the variational autoencoder gets its name from. So what do we do with this? We really wanted to maximize this evidence here, but we cannot compute it. We do know this thing is smaller than it, so we'll just maximize this one and then hope that the evidence the log likelihood gets pushed up. And there is also reason to have hope that this will be useful, because I think in one of the lectures it was mentioned that under some conditions we can actually get this inequality to be an equality. It depends on how closely I think it depends on how closely the approximate posterior correspond to the true posterior. So this is not going to be the case for us, but it's just extra motivation why this is a good idea. Okay, so we're gonna try to maximize this, which means our loss, which we have to minimize, is just the negation of it. Let's also take a bit of time to understand kind of pieces of this loss. Let's talk about the first term, in particular this bit. This bit means for a fixed latent, we want the likelihood of the data on which we are measuring the loss to be high according to our model. And then this is, I guess, considering the expectation here, the latents are coming from our encoder. So the process, I guess, basically this is the reconstruction process where you go take your input, turn it in, get your distribution over latents, and then sample from that, and you want those. You turn it into a distribution over your latents, and then you want the true data to be likely according to that distribution. So it kind of captures trying to reconstruct the input faithfully. The second bit, the KL term, is kind of like a regularization term. It, I guess, punishes the posterior from going too far away from the prior. And this formula does have an expectation. In practice, we just take some samples, sometimes just one. I guess in our case, it will be just one. Sometimes you can take a few more. So I do want to go back to our diagram to help motivate this and talk through, I guess, what happens, how we get this distribution from our autoencoder, the sampling distribution. So we have this prior here, and we're just going to take, according to the normal distribution, samples here, decode them, and this will give us some distribution here, right? In practice, when we are training or when you're reconstructing, we just have examples of images get mapped to various sections of this latent space, and we check that those get, I guess, roughly reconstructed well, right? So again, there's this question of holes when we want to sample from the variational autoencoder. If some space, say here, was not really covered by any of the input images and their learned distributions especially, then when we're sampling from there, I guess as you saw in the autoencoder case, it's not clear it's not, I guess the network would not have been trained so well there, so it's not clear exactly what you're getting. So we have that second term with the KL to try to get all these distributions to kind of fill this prior space nicely, so that when we're sampling, we get nice results. I think that's roughly like a high-level explanation over what the loss is and what it does. Maybe it's time for a question. Okay, there does not seem to be. Stan, I don't know, are there some questions to discuss generally?
Any new questions? We did discuss it with some previous questions of the chat, but they're probably a bit more specific.
Okay.
There was a question about, do you have any recommendation, David, for a resource to learn in depth about generative models? And that source would be up to date with state-of-the-art solutions.
So generative models in general or variational autoencoders?
I think the question by Wojtek was about generative models in general.
Okay, so I guess I can try to gather some and message you later. potentially. Though I don't have anything off the top of my head for sure. Cool. So let's. There's not that much time, so I think we can go through the implementation a bit faster, so that we get to see the latent space and the variation out encoder as well. So first of all, I guess just to for actually implementing the loss, we do have this KL term here, which in general between two distributions is not analytically. You don't have an analytical equation for it or computation, but since in our case the prior and the posterior are Gaussian, you can actually just calculate it like this, element-wise on the latent space. So the first exercise is just to implement this formula. So for the sake of time, I'm actually just going to copy that in, and then we can discuss it. Yeah, so it's literally an implementation of this formula, which just involves the variance and the log of the variance of the posterior distribution that we're learning, as well as the mean of it. Okay, I'll leave it on the screen for a little while. I guess you can also copy it over from the solutions. I'll leave it here in case someone doesn't have that open. Okay. In the next cell, again, the only exercise to do is to take the log likelihood that was already calculated and the KL that's already calculated, and then return or calculate the elbow from these above components. So going back to the formula, the elbow was basically the log likelihood minus the KL. And let's see. So elbow is the log likelihood minus the KL. Cool. We run some checks. Great. And now let's start training. This is all written for you. So let's just start it up and then we can talk about it a bit.
And while it is running, as we are getting closer to the finishing time, so I suppose we'll leave the last question as the homework as well.
By the last question,
I mean the last task. Sorry.
Yeah. Yeah, I think we can.
Yeah.
Oh. Yeah. I guess I'll quickly kind of go over it to see what's there. Yeah. So in terms of what the code is doing, I mentioned that we want to quantize the our images. And let me just show that a bit better. So this training loop is very much like, or almost exactly like the autoencoder one. Really, the main difference here is that when we take some image, say on the validation set, I sample from it with a, interpret the pixel as a Bernoulli distribution and then sample from that. So that's going to be, I guess, pretty pixelated, but that's the input. And then running over the same image multiple times, you always take different samples. So I guess the model still gets a sense of what the original image looked like. And other possibility here is you can take your original image and then kind of make it black and white. If you can succeed doing that in a way that you can still make out that, like, if it's a bag or not, that's also a possibility. Or you can do somewhere in between. Okay. All right, at least my variational autoencoder has trained, and we have plotted the elbow, the log likelihood, and the KL as well. So just to recall, the elbow that we are trying to maximize is indeed going up, so that's a good sign. The log likelihood, and the elbow is the log likelihood minus the KL. So an interesting thing that you might observe is that the KL initially goes up, even though it shows up in the, even though I guess technically lower values are better. But then later on it actually starts decreasing, and that's because in the elbow you kind of need to, you have these two terms, and these two terms are somewhat at odds with each other. Basically, one of them is trying to make it so that your reconstruction is good. The other is trying to pack all of your latents close to the normal, which might be at odds, and it looks like it is, since this is decreasing here. And we can again look at some reconstructions. They look fairly similar to the autoencoder here. We can also actually look at sampled images, and as you can tell, these don't look so great, but you can still kind of make out the shape. But this is actually what the network is seeing as input. Yeah, so normally people actually use mean images, or sometimes you can use not the Bernoulli distribution to model your data, but potentially I think a Gaussian, or you can discretize, quantize your data not just to 0 and 1, and then use multi-class. Cool. And I guess in about 5 minutes, I just skimmed through the latent spaces. Perhaps there's, yeah, I guess there's not three questions, so that's fine. So recall that we wanted our sampling distribution to be like the true data, and similarly, I guess we just talked about it. The KL component of the loss is trying to keep our encoded latents, that we get from the encoder close to the normal distribution. So in a sense, you would expect that potentially the latents that we visualize for our examples, they should be kind of similarly distributed to a normal. Okay. Oh, I guess it already ran. And yeah, so this is what the latent space looks like. If we kind of imagine a normal distribution on here, I guess the one sigma variance would be something like this. So that area is well covered. But before I answer before I answer the questions here, let's look at them. So do you expect samples, i.e. decoded latents from the normal distribution to be good? Do you expect samples to be actually similarly distributed to the real data, and why or why not would you expect that? And can you think of some examples that would affect how similar this distribution looks to the prior? These could be ways to parameterize, train, or a variational autoencoder, or even introduce new parameters, maybe tweaking the trade-off between the reconstruction and sampling. Yeah, so maybe just looking at this a little bit. Do you want to say something?
No.
Okay.
It looks nice. It's like a butterfly or something.
Yeah, it exactly looks like a butterfly, and I'm surprised because multiple reruns also look like a butterfly. Could be a new theorem.
That's a prior. Okay.
Yeah. So one thing I noticed is for one of these classes, they are very far away. So in a sense, I would probably not expect sampling to show me things like that class. Though at the same time, it is also true that a lot of classes do look similar. So maybe that's where some of the confusion comes from. Okay, and then in terms of, this is a very open-ended question on things that would affect what this distribution looks like. Again, having more powerful decoders would probably allow us to pack more things closer to their prior. An interesting idea would be to add the parameter to the KL term, with which you can actually tweak just how important you think that KL is, and with that you can control how tightly these things will be packed as well. Yeah, those are just some of the answers, or some potential answers. Cool. And then the other thing that's here is we take a grid over the latent space and then just decode all of them. So this grid right now corresponds to kind of from something like this grid, right? And we take a grid on that area and then just decode them and see what they look like. And I think it's quite cool because you can see these changes through classes. So you get the shoes and probably sandals around here, which turn into boots, which then turn into, I guess this is a bit harder here, turn into some of the, probably a coat, and so on, finally going into trousers. So I guess the nice thing is kind of the network kind of figures out how to smoothly transition from things that look similar to other things. And there's also another variant of this plot where we actually sample. We actually show tweak the grid so that it's more like sampling from the prior. So you can see on the x and y axis that we kind of blow up the center of that grid. Yeah, and can explore the latent space that way as well. For the last 1 or 2 minutes, Stan, would you go over the regularized autoencoder, or should I just do it?
Please go. So you keep you sharing the screen. I think that's would be
okay. Cool. Yeah.
I will just make one comment. There was a question on the Rocket chat. Does it make sense to use the noising idea from the noising autoencoder with VAE? So to bring everyone up to speed on the same page, the noising autoencoders add noise to the input before decoding it, and that's another form of introducing information bottleneck. And this homework is connected to this question in the sense that how you can see VAE is like an autoencoder where you add noise, but to the hidden space. That's one way to view VAE, a very maybe unorthodox one, but you can see it like that. And that's what introduces the information bottleneck. And this homework will be dealing with trying to train an autoencoder without the variational part, which is a bit complex to think about and implement, but still being able to produce good samples. Yeah, over to you, Dave.
Yeah, I think that the homework ties a lot of these ideas that we talked about and explored, ties them together very nicely. So I guess a question you might have is whether vanilla autoencoders then generate visually good samples, how they compare to various autoencoders. And I guess we're not necessarily concerned with modeling the true data distribution as closely as in the variational autoencoder, where that was part of the motivation. And the authors of this paper that we are working with here argue that the answer is yes. Basically, they argue that by adding a little bit of regularization instead of the variational mechanism, just adding some regularization to the autoencoder, and then estimating some basically density on the latent, basically estimating the density of the latent codes, we can get high quality samples. And this is kind of something we alluded to earlier already. So we do encourage you to check the paper out. I think it would be nice to read after this tutorial, and we also hope that the exercise is useful. So in terms of the exercise, again, this is more open-ended. The first thing is to investigate how the samples look when you use a latent size of 2 versus 50, and kind of try to think about why that is. Implement the regulars autoencoder by, I guess they have a few variants. You can pick one of them, or I think this one will refer to one. And investigate whether this added regularization improves the quality of the generated samples when coupled with ex-post density estimation. So this ex-post density estimation is looking at the density of your latents and then just fitting that with, say, a Gaussian or mixture of Gaussian or something else. And investigating whether this added regularization reduces mean squared error on the validation set. And I guess since you are regularizing, it has some parameter, so you probably want to tweak that a little bit and see what the effect is. Okay, and to help you get started, we did provide some code here, which trains, I guess, for now an autoencoder. You will have to add the regularization to it. There's a very simple ex-post density estimation here where you just take the mean and the standard deviation of the latents and fit a single Gaussian. And then finally, you can check the reconstructions here. I guess as a kind of a tip, if you're working with higher dimensional latents, you probably want to use Disney to visualize what that looks like. Yeah, I think that's about it. Oh, I forgot one thing. I do have a little bit of further reading included at the end there that are about VAs and how they behave. Basically, some of the things that we started thinking about, people have done, I guess, large studies on or are trying to investigate as well. And there's some papers related to that here, in case you're interested. Cool. Stan, do you want to add something, or should we say bye?
Well, I just wanted to say thanks everyone for joining. It's a bit already late in Poland, as far as I can tell. And, hope you have learned something. Feel free to reach with any questions, and we'll talk about the homework on Monday. Yeah.
Yeah. Thank you.
Thanks a lot, everyone.
I am online again. Thank you so much, David and Stanislaw, for the great tutorial. I saw on Rocket Chat that you're already writing papers together and discovered new ideas, so that's really awesome. Okay, so I've just connected a bit just for a few announcements. So first of all, so I hope you've seen that for the unconference proposals, the deadline is tonight at midnight Poland time. And we've reduced the number of members that you need to have in a team. So with 5 people, you're good to propose an idea. Second, please post questions on Slido for next